Okay, so am I audible, right? Hello everyone, am I audible? Okay, so hope am I audible, right? So okay, thank you. So hello everyone, I am Subrata Samanta and I am one of the TA for the thermal physics course that is taken by Professor Demarla Banerjee in this semesters at NPTEL. Okay, so this is the fourth session in this series. Okay. And today I will solve the week 4 assignment problems. Okay, so basically I will solve previous year assignment problems, week 4. Okay, assignment problems. Okay, at the end I hope you are able to calculate solve this week assignment problems. Okay. And in the meantime, if you have any question, any doubt, okay, you can also ask. Okay, or if you have any questions, okay, from the week content, okay, so you can also ask these questions. Okay, and I hope you are also watching the lectures, okay, in a regular basis. So let's share my screen first, then if you have ask any questions you can ask. Yeah, I hope my screen is visible, right? My screen is visible, right? Yeah, so if you have any if you have any questions, you are also welcome to ask. Any questions from the previous week or this week assignments, okay, or week content, okay. So you have any questions, you can ask now, okay, or you can ask in the middle as well. Okay, it seems that there is no question, so I will start the sessions. Okay, so let's look into the first problems. Okay, I'll solve 10 problems, okay, in the previous year assignment, week 4 assignment problems, that is related to the Brownian motions, okay, and related stuff. Okay, so the first problem, so an experiment with the colloidal particles. So let's first open the marker. Yeah, so in the first problem, so an experiment with a colloidal particle suspended in a liquid at temperature 30 degrees centigrade shows that the mean square displacement per unit time to be 1.5 centimeter square per second. Find the radius of a suspended particle. Okay, where the viscosity, the coefficient of viscosity is given and the number of Avogadro number is given, right? So okay, so how to calculate the radius of a suspended particle? So first identify that what is the given. So temperature is given, so that means T temperature is 30 degrees centigrade, that means 273 plus 30 Kelvin, right? So 303 Kelvin, and then the mean square displacement per unit time. Okay, so mean square displacement means that, let's say S square and then average, right? So S is the distance, okay, or I can write in this way that delta x is the distance square and then average. Okay, so that is given per unit time is 1.5 centimeter square, right? Let's say per unit time, per, let's say time is tau is 1, okay, 1 second. So this is your time, okay. So if tau is 1 second, then your delta x square is 1.5 centimeter square. Okay, that is basically the statement is that the mean square distance displacement per unit time. So time your unit, so I consider tau is 1 second and delta x square is 1.5 centimeter square. Okay, well, this is the dimension of this is length square, right, centimeter square. So dimensionally match, and we have to calculate the radius, okay, r. We have to calculate the radius of a suspended particles. where the coefficient of viscosity eta is given. Okay, so since all of these are in the CGS unit, so I will use the CGS unit because answer is also given in the CGS unit. Okay, so from the beginning I will use the CGS unit. Okay, so every quantity I replace in the CGS unit. So let's first solve this problem. So if you know that the Einstein equations, right? So you know the Einstein equations of mean square displacement of a Brownian particle. So what is this equation? Now if you consider the Einstein equations, so Einstein equation of, so question 1, so the Einstein equations of mean square displacement of a Brownian particle is basically delta x square, right? So delta x, the mean square displacement, is equals to kbt over 3 pi eta r times your collision time, okay, time interval, right? So this is a time interval tau, and this eta is the coefficient of viscosity. So I am clearly written that. So eta is your coefficient of viscosity, right? So what is the unit of eta? So in SI unit, so eta is basically, what is the unit of eta in SI unit? Is Newton second over meter square in SI, right? So this is basically Pascal times second, right? So Newton per meter square is a Pascal times second, okay, in SI unit, and so in SI, and in CGS, so eta in CGS is basically POIS, okay, so POISE in CGS unit. Okay. So the next one is the temperature T. So T is Kelvin. Okay, so T is Kelvin. Let's say given the temperature is given, so T is Kelvin. Okay, and let's say is that Kelvin, and R is the, I will use CGS unit, so is centimeter. Okay, CGS unit, and tau is second, right? So tau is the time, so units is second. Okay, so eta is given, and okay, so this is the mean square displacement. So this is the mean square displacement. So this is a delta x, so it's a 1d, so mean square displacement in 1d, okay, in time tau. So in time tau, the displacement, mean square displacement, is delta x square, right? So now in the problem, so this, the values of delta x square is given. So delta x square is given. So what is the value? 1.5 centimeter square and tau 1 second. So when 1.5 centimeter square, when tau equals to 1 second, right, and the coefficient of viscosity eta is 0.0, what is the value? 0.01 POIS, right? Yes, and the temperature 303 Kelvin. So temperature is 303 Kelvin, so 0.01 POIS, and the temperature T is 303 Kelvin. Okay. Yes, and the values of Kb is you know that the Kb is basically the Boltzmann constant, so 1.38 into 10 to the power minus 16, right? So in CGS unit, okay. So in SI units is basically 10 to the power minus 23 joule per Kelvin, but in CGS unit is 10 to the power minus 16. So I'll use the CGS unit. okay. And yeah, so and we know the values of pi, okay, it's 3.14. So just plugging these values, okay. So the r, basically then kbt over yeah 3 pi eta delta x square, 3 pi eta delta x square times your tau, right, tau. So now kb value you know 1.38. So this kb is a Boltzmann constant, and 10 to the power minus 16 times temperature 303 Kelvin, okay, divided by 3 times pi is 3.14, right, and your eta is 0.01 poise in CGS unit, and your delta x is 1.5 centimeter square in CGS unit, and eta is 1, sorry, tau is 1, okay. So yeah, so you just calculate in the calculator, so that gives 0.29 times 10 to the power minus 12, so what is the unit? So unit is CGS unit, so is centimeter, right. Yes. So now check the answers, okay, if the if this answer is given in the options or not. Yes, so basically the option is a 0.29 times 10 to the power minus 12, right. So the A option is right. Yeah, so now so this is the, then this is the correct, okay, so this is the correct. So now the second problems. So the second one, yeah, so far any questions? Okay, so then I move to the next one. So the second question is that, so the horizontal displacement of a given particle, okay, in a water for 11 successive intervals. So 11 successive intervals, each of 30-second duration. Okay. So first note down that 11 successive intervals, that means n equals to 11, and tau for each intervals there are 30-second durations. Okay, so 30-second. Okay, and this 11 successive interval, the distance, the horizontal displacement is 0, 5.6, minus 4.7, blah blah blah, times 10 to the minus 4 centimeters. So you know that what is your delta x1 is 0, delta x2 is 5.6, right, and delta, yeah, so delta x3 minus 4.7 dot dot dot, okay. So delta x11 in this way, so the last one, the delta x11, okay, so all are is times 10 to the power minus 4 centimeter times 10 to the power minus 4 centimeter, and this is 0 centimeter delta x1, and delta x11, so in this way dot dot dot, and at the last one, the delta x11 is basically 16.0 times 10 to the power minus 4 centimeter, right, okay. And the temperature was 18 degrees centigrade, so the temperature T is 18 plus 273, okay, change to Kelvin, so this one is Kelvin, okay. So it gives if 2293, so is 291, right, so 291 Kelvin. And the viscosity of water at 18 degrees centigrade, the same temperatures, is 0.1 poise. So eta, the coefficient of viscosity, is 0.1 poise. Okay, again I use CGS unit because all are given in the CGS unit. Okay. If the Avogadro number to be 6.0 times 10 to the power 23, calculate the radius of the particles. Okay. So, the same questions as in before, calculate the radius of the particles, but in this case the mean square displacement per unit time is not given. Okay. So, you have to calculate first mean square displacement, okay, where the data is given is delta x1, delta x2, this kind of data is given. So, you have to first calculate the mean square displacement, okay. Then we calculate the radius of the particles as we do in the previous questions, right. Okay. So, how to calculate the mean square displacement? So, the mean square displacement, the calculation is very easy. So, the mean square displacement you can calculate in this as delta x square and their average, because the average of delta x square is basically how many successive intervals, n, right. So, capital N, if there is a n successive intervals and I goes to 1 to capital N, okay, and then delta x I for each interval, what is the displacement? Horizontal displacement, because we are considering x only one variable. So, it's a 1D horizontal distance and that is delta x square, okay, delta xi for each interval square, okay. So, delta xi square and I goes to 1 to n. So, what is the values of n in this case? So, n is 11 and we know delta x 1 0, delta x 2 some 5.6 times 10 to the power minus 4 centimeter dot dot dot, okay. So, if you plug these values, okay, so this basically your 1 over 11 times 0 plus 5.6 square plus, okay, so let us 10 to the power minus 4 taken outside. So, 10 to the power minus 4 and the square of it is 10 to the power minus 8, right. So, 1 over 11 and 10 to the power minus 8, okay. So, I will take 10 to the power minus 8 outside of the bracket. So, and in the inside the bracket is 0 plus delta x1 5.6. So, delta x2 4.7 and square, okay. So, the negative sign is basically when you take a square is positive, plus, okay. So, plus if you write in this way, plus is 10.8 square plus 6.6 square plus 9.8 square plus 11.2 square, okay. So, I am not writing minus sign, okay, because when we performing square, so it is already plus, okay. So, that is why I am omitting the minus sign, and then 4 square plus 15 square plus 19.1 square, and the last one is 16 square, right, and the unit is centimeter square, okay. So, now if you use your calculators, okay, to calculate the sum, okay. So, at the end you got 1.117.9 10 to the power minus 8 centimeter square. So, please check these answers, okay. So, now once you know that the values of this delta x square average, okay, for the tau is basically is 30 second, right. So, tau is already given in the problem. Yes, so this is basically each of 30 second duration, that means the time interval, okay, tau. So, tau is 30 second and we know the delta x square, okay. So, now same as before, okay, same as before. So, if we use the Einstein equations, so delta x square average is equals to kBT over 3 pi eta r times tau. So from this r equals to the radius of the particles is equals to kbt times 3 pi eta times delta x square, then average, okay, times tau. So plug these values. Okay, so kb we know in CGS unit, so here I am also using CGS unit, so 1.38 times 10 to the power minus 16 in CGS unit, okay, basically arc per Kelvin, and 291 your temperatures, okay, and what is the tau? So this is basically tau, so tau is 30 second, so 30 divided by 3 times pi 3.14 times eta, so eta is 0.1 poise in CGS unit, okay, and what is the delta x square? We just calculated this value, so it's 117.9 10 to the power minus 8, okay. Since I am using all in the CGS unit, so the unit of r is centimeter, right? So use your calculators, okay, and calculate the values, okay. So it gives 1.08 times 10 to the power minus 6 centimeter, okay. So let's check this is in the option or not. 1.08 into 10 to the power minus 6, yeah, so the problem 2, 1.08 into 10 to the power minus 6, so the option C, right? So option C is correct. Yeah, so any questions, any doubts? Okay, if not, then I'll move to the next question. Okay, so the next question, so in his experiment of water suspensions of gamboge at 20 centigrade, okay, Perrin observed an average of 49 particles. So first the temperature is 20, so T is 20 plus 273 equals to 293 Kelvin. Perrin observed an average of 49 particles per unit area in a layer at one level and 40 particles per unit area at a level of 60 microns, okay. Calculate the effective mass of each particles, okay. So how to calculate? Okay, so this is basically there is a two level, okay. So for the first level the 49 particles and the second level 40 particles per unit area, right? That means, so particles per unit area, that means the number density, right? So particles per unit area, so that means the number density. So that means, let's say I know that for n the number density at height, the level height h1 is 49, okay. So this is, let's say height is z1, okay, and the number density n at level of height z2 is basically 40, right? So now we know that how the number density changes with height, right? So in the class, this discussed that pressure P at height Z1 is sorry, at height Z2 is equals to pressure. So this P is pressure at height Z1 times e to the power minus mg. So this is, let's say, m. Okay, so the mass of the particles times g times, sorry, Z2 minus Z1, the difference between these two height, okay, level, divided by kVt. Okay, and this is the your effective mass of the particle, each particles. So this m is the effective mass of each particles. Since the pressure is proportional to the number density, so the number density also follow the same thing. So n at Z2 equals to n at Z1 times e to the power minus m g, and then Z2 minus Z1 divided by kVt. Okay, but the m is the effective mass of each particle, effective mass of each particle. So we have to calculate the values of m. Okay, provided that nz2 is provided, nz1 is provided. So nz2 is given, nz1 is given, and g value we know, and z2 minus z1 is also provided. Okay, so the z2 minus z1 is that 60 microns. Okay, so the 49 particles at one level and the 40 particles at the level of 60 microns. Okay, higher. Okay, so this is important, the 60 micron higher. So that means it's z2 minus z1. Okay, it's basically 16 micron, right? Sorry, what is it? 60 microns. So I'll change it into which units? In this case I will use yeah, so in this case I will use SI units, because the answer is given in the SI unit, right? Kg. So I will use SI unit. So 60 micron to in SI unit we change this 10 to the power minus 6, right, meter. Okay. So 1 micrometer is 10 to the power minus 6 meter. So this Z2 minus Z1 is 60 times 10 to the power minus 6. And we know that what is the values of kb and t is given, right? So we calculate m. Okay, so now we calculate explicitly. So your third problem, so it's basically n at z2 equals to n at z1 times e to the power minus m g z2 minus z1 over kVt. So if we take log on both sides, so log base e, so it's ln is n. So n at z2 I will call n at z2 I will call n2. Okay, and n at z1 I will call n1. Okay, so n2 over n1 ln, okay, is equals to minus m g z2 minus z1 over kVt. Okay, and if you know that ln a by b is equals to minus ln b by a, right? So then m equals to mg times z2 minus z1 over kVt is equals to ln n1 over n2, right? So m equals to kVt over g times z2 minus z1 times ln n1 over n2, right? So we plug these values. What is the values of Kb in SI unit? Okay, so the values of Kb in SI unit is 1.38 times 10 to the power minus 23 joule per Kelvin times temperature T. What is the temperature? 293, right? So 293 Kelvin. Please cross check this value. Okay, and okay, so divided by G value, the values of G in SI unit is 9.8 and Z2 minus Z1. So I already see the 60 micron. So in SI unit 60 times 10 to the power minus 6 meter times ln n1 over n2, right? So ln 49 n1 and n2 is 40. So now if you use your calculator, okay, and calculate this value, so it gives 8.6 times 10 to the power minus 18 kg. Okay, so please cross check this value. Okay, use your calculator. Okay, so let's check this is in the option or not. So 8.6 times 10 to the power minus 18. Yeah, so the last one. So the option D is correct. Okay. Okay, so far any questions, any doubt? So the average 49 particles per unit area in a layer, that means it's basically number density. Okay. Okay, so it seems there is a no question. Okay, so I will move to the next one. This is 3. Yeah, so fourth one. So the object on, so let's just mark this. Yeah, so observations on Brownian motion of a spherical particle of radius. Okay, so in this case the radius is given. So first note down that what is the values are given. Okay, so the radius r is 0.4 times 10 to the power minus 6 meter is given, okay, in SI unit. Okay, fine. And at temperature 27 degrees centigrade, so temperature T 27 plus 273 Kelvin. Okay, so it's basically 300 Kelvin. And viscosity again, okay, so the viscosity in this case is given in the SI unit, right? So Newton second per meter square, so 10 to the power minus 3 Newton second per meter square. So that is basically Pascal second, right? If the value of mean square displacement is in 2 seconds, okay, so tau is 2 seconds, okay, and the mean square displacement, that means delta x square, okay, so this is the mean value, so mean average, so that is given 1.78 times 10 to the power minus 12 meter square, right? Yeah, so please correct me if I wrong. Okay, 1.78 times 10 to the power minus 12 meter square. Yes, then compute the value of Avogadro number Na. So in this case we have to compute the Avogadro number. Okay, we already know the values of this number, but want to calculate the Avogadro number in this process. Okay. Yes. So again we use the same formula, the Einstein equations. Okay. So again we use the Einstein equation. So the problem 4. So the Einstein equations, again we use Einstein equations. Okay. So it's basically delta x square, then average is kbt over 3 pi eta r times tau. Okay. So now we see that there is a no NA Avogadro number. Okay. So how to compute the Avogadro number? Because in this equation there is a no NA. Okay. So NA is the Avogadro number, right? So NA is the Avogadro number. But in this equation there is a no Avogadro number. N is there. So how to compute the N? Can anyone tell me? So tau given, R given, eta given, temperature given. How to compute the Avogadro number? Because there is a no NA in these equations. So what is the Sarbajonin gas constant? So we know the Sarbajonin gas constant R basically NA times Kb, right? So Kb is a Boltzmann constant, right? So you have to replace this Kb by Sarbajonin gas constant. Okay, so I mean sorry, it's a universal gas constant. Okay, so this is universal gas constant. Right. So this is a universal gas constant R, and Kb is a Boltzmann constant and Na is a Avogadro number. Since we want to calculate the Avogadro number, so you have to replace Kb by universal gas constant R. Okay. So that means the delta x square average of this is equals to RT over Na times tau over 3 pi eta R. So now in this case we have to Na is basically your RT times tau over 3 pi eta R times delta x square and then average. Okay. So what is the values of R in SI unit? Since I am using SI unit, so what is the values of R in SI unit? 8.314, right, times the temperature 293. So what is the temperature? Okay, so let me check once. 27. So temperature is 300 Kelvin. Sorry. So temperature is not 293. So temperature is 300 Kelvin. Okay. Times, what is the values of tau? It's 2 seconds, right? And 3 times values of pi, 3.14. And what is the values of eta in SI units, right? It's 0.4 times, no, what is the values of eta and R? Yeah, so eta value is 10 to the power minus 3 and r value is 0.4 times 10 to the power minus 6. So the values of eta is 10 to the power minus 3 and r value is 0.4 times 10 to the power minus 6, all are in the SI unit. Okay, so unit careful. Okay, times delta x square. Okay. So it's 1.78 times 10 to the power minus 2. So all in the denominator. Okay. So all in the denominator, and it gives 7.4 times 10 to the power 23 mole inverse, right? Okay. So that is the Avogadro number, and we know what is the values of Avogadro number, 6.023, right? Slightly higher value. Yeah. So let's see this is in the option or not. Okay. So according to the problem, these observations. Okay. So according to this observation, so the Avogadro number we found is basically 7.4 times 10 to the power 23. This one. Okay. So the answer is B. So it's not necessarily that the Avogadro number should be 6.3 or 6.023 times. We know the Avogadro number is 6.022 times. So this is the average value 10 to the power 23, right? That is not necessarily true in these observations, right? So you have to calculate the Avogadro number, okay, using the Einstein formula. So this is the options. Okay, so the B. Okay, so far any question? Okay, if not, then I will move to the next one. Okay, so in the next question, the 5. Okay. So the horizontal displacement of a Brownian particle, okay, in a medium at temperature 20 degrees centigrade in 11 successive intervals. So again 11 successive interval of 30 seconds. So n equals to 11, right? And tau is 30 seconds, right? And the temperature is 20 degrees centigrade. So temperature T 20 degrees centigrade, that means 20 plus 273, right? So 273 Kelvin is 293 Kelvin. Okay, and the horizontal displacement of a Brownian particle in medium is in 11 successive intervals of 30 seconds at 0, 5.6, blah blah blah. Okay, and 16 micrometer. So that means delta x1 is 0, delta x2 is 5.6 times, so this is the micrometer, and delta x3 is how much, 4.7 minus 4.7 micrometer, and blah blah blah. So the data is all same as in the before, right? So if you look into the problem 2, if you look into the problem number 2, right? So here you see that the 30-second durations, 11 successive interval, and the number is 0, 5.6, minus 4.7 into 10 to the power minus 4 centimeter, right? Right. So delta x1 is, delta x2 is 5.6 into 10 to the power minus 4, delta x3 is minus 4.7 into 10 to the power minus 4 centimeter. But here the number are same. So 5.6 micrometer, if we change into the centimeter, so it's basically 5.6 times 10 to the power minus 4 centimeter, right? Since 1 micrometer is 10 to the power minus 6 meter, right, and 1 meter is basically 10 to the power 2 centimeter. So 1 meter is 10 to the power 2 centimeter, so it's 10 to the power minus 4 centimeter. So 1 micrometer equals to 10 to the power minus 4 centimeter, right? So that means the number are same, right? So we already calculated the delta x square in case of this, okay? So you already know that what is the values of this delta x square average, okay? So delta x square average. So you just copy from this. So the delta x square we already calculated here, right? So it's 117.9 times 10 to the power minus 8 meter square, okay? Yeah, sorry, centimeter square. So we convert into a SI unit, since that in this problem we are using in this problem the answer is given in the SI unit, okay? So I will use the SI unit in this case. Okay, so the problem number 5, so I will use SI unit. So delta x square average is 117.9 times 10 to the power minus 8 centimeter square. So if we change into the meter square, what is the value? It's 117.9 times 10 to the power minus 8. So 1 centimeter equals to 10 to the power minus 2 meter, right? So it's 10 to the power minus 4 meter square, right? So if you multiply this, so 117.9 10 to the power minus 12 meter square, right? Okay, we know that what is the values of delta x square, and we know in the time is tau is 30 seconds, okay? So now we have to calculate diffusion coefficient of the medium, okay? For the temperature is 293 Kelvin. So how to calculate the diffusion coefficient given delta x square, the mean square displacement, and the successive time intervals, okay, 30 seconds. So tau is given 30 seconds, and your delta x square you know. How to calculate diffusion coefficient, okay? So the diffusion coefficient is given by d equals to, so if you look into, so recall your class notes, okay? So the diffusion coefficient d is equal is delta x square average over 2 tau. That's very simple, okay? So only we need two informations, okay? Tau and delta x square. So temperature information is not needed, okay, to compute the diffusion coefficient only, okay? So if you plug these values, okay, so it's basically 117.9 times 10 to the power minus 12 and 2 times 30. So what is the unit? of the diffusion coefficient, tau is second, and delta x square is meter square, so meter square per second. So yeah, so now if you use your calculator, okay, so it gives 1.965 times 10 to the power minus 12, right, at meter square per second. So let's check this is in the option or not. 1.965 times 10 to the power minus 12. Yeah, the first one. So option A is correct. Okay. Okay, so far any question? Okay, you can also write the questions if you have any questions. Okay, you can also raise your questions in the chat box. Okay. Okay, so it seems there is no question, so I'll move to the next one. Yeah, so the next one is the problem number 6. So the pressure at sea level, okay, at 27 degrees centigrade is, the value is given 1013. So first note down the temperature. So T is 27 degrees centigrade. So it's 27 plus 273, right? So it's basically 300 Kelvin, and your pressure is P. So I denoted the pressure at sea level is P naught. Okay. Yeah, and the temperature is T naught. Okay, at sea level temperature. Okay, and pressure is P naught is 101,325 Newton per meter square, right? So this is in the SI minute. Okay, at certain height, the pressure, so basically a certain height from the sea level. Okay, so this is your sea level. And the certain height, let's say P1, the pressure is 1/16 P naught, right? So at certain height, the pressure is 1/16 times the pressure at sea level. So at pressure at sea level, we denote P naught. Okay, so this is the pressure at sea level, and this is the pressure at certain height. Okay, if the temperature increase 4 times, then what is the pressure at that height? Okay, okay. So read the question carefully. So the pressure at sea level is given, okay, and we have to calculate the pressure at some height from the sea level. Let's say H1 is the height. Okay, right, but it's already given that the H1 at the height, the pressure is 1/16 over P naught from the sea level. But now if the temperature increase 4 times, okay, then what is the change of pressure at that height? Right. So question clear on me. So you know P naught at sea level pressure, and at height P1, at certain height H1, okay, from the sea level, the pressure is P1 is given, is P naught over 16. Okay. Now if we change the temperature, okay, so if we change the if we increase the temperature 4 times, so then what is the pressure at that height, at the height H1? So that means how this number change P naught over 16 changes when the temperature increase 4 times. Okay. So how this number, or what is the number, okay, at the end when we change the temperature 4 times, okay, increase 4 times, okay. So how to compute? So you know that pressure at, let's say, height H1, okay, and pressure at sea level P naught is related to e to the power minus m g, right. So this is a small m, the mass of particles, g times h height, let's say h1, and we denoted the sea level height is 0, okay, or let's say h0. So this is your sea level height h0, and this is one h1 divided by kVt, okay, and that is given is P naught over 16, that is given. So at height h1, some height h1, P1 is given P naught over 16, right. So that means we cancel this P naught, so basically your yeah, so basically the values of this exponential are e to the power minus mg h1 minus h0 over kVt is equals to 1 over 60, right. So now we change the temperature, since this quantity depends on the temperatures, right. So now we increase the temperature 4 times. So if we increase the temperature 4 times, so that means your so basically T to 40 T to 40, then the pressure is P1 to P2. Okay. We know at that height H1 the pressure is P1, but now its P1 changes to P2 when the temperature T is changes to 40. So then the P2 is basically P naught times e to the power minus mg h1 minus h0 over temperature changes, so 40, so 4 kVt, right. This is basically P naught times e to the power minus mg h1 minus h0 over kVt times 1 over 4. Okay, we can write this in this form, okay, because it's exponential, so I'm writing to the power of 1 over 4, right. So now I know what is the values of this, so this one, right, this one, so it's actually same, e to the power minus mg h1 over h1 minus h0 over kVt. So plug this value here. So P naught times 1 over 16 to the power 1 over 4, right? So what is the value? So that means, so 2 to the power 4 is 16, right? So that means 16 to the power 1 over 4 is 2. So it gives P naught over 2. So therefore the pressure changes at the height h1. Okay. So the pressure changes at height h1 is basically P naught over 16 to P naught over 2, right, when temperature T to 40, right. When the temperature changes T to 40, the pressure at that height, it changes P naught over 16 to P naught over 2. That means pressure increases, right. So let's see this is in the option or not. So P naught over 2. Now you know what is the values of P naught. So 101. So it changes P naught over 2. So P naught value is 101325. So if we divided by 2, 101325 divided by 2. So it basically gives 50663 and dot dot dot. Okay. So approximate answer this. Okay. So C is very close to C. Right. So approximate. This is basically, yeah. Yeah, so far any question? Okay, how many questions left? 6, 7, 8, yeah, 4 questions are left. Okay. Okay, so if you have any question, please ask. Sorry. Yeah, so it seems there is no question. So I'll move to the next one. Okay. So the next problem is the problem number 7. So in which case the motion of the Brownian particle is greater? Okay. So how to increase the motions of a Brownian particle? So first of all, the Brownian motions are random, right? So random motions and then continuous motions, right? And how to increase the motions? Okay. What are the way to increase the motions of Brownian particles? So recall your class notes. Okay. How to increase the motions of Brownian particles? Increase the motions of a Brownian particles. So first of all, the boundary particles are random continuous below, right? Step 1, smaller particle size, right? So if the particle size are small, so smaller the particle size, so smaller the particle size, right? So that increase your motions or greater the motions. Second, lower the viscosity of the medium, right? So lower the viscosity of the medium, right? How do I know these kind of things? Since we know that delta x square average is basically kBt over 3 pi eta r times tau. So that means r means the radius of the particles, right? So if we reduce the particle size, that means you have to reduce the radius r, right? So that is the first one. So smaller the particle size, or if you reduce the values of r, so that increases the delta x square, right? So if r decreases, so that means lower the values, reduce, okay, delta x square average value increases, provided other are fixed, okay. Second one, lower the viscosity if eta reduce, since they are denominator, okay. So eta is reduced, delta x square is also increases. So this arrow is basically increases upwards, and the arrow in the downwards is basically decreases, okay. So if we decrease radius, so it increases the values of delta x square, right? The average, the mean square displacement, that means the velocity increases, okay? And if we decrease the values of eta, also the delta x square increases, since they are in the denominator, okay? Third one is the temperature. So temperature is the numerator, so that means the temperature increases, delta x square is increases, or in other words, the temperature decreases, delta x square decreases, right? Since I am talking about the how to increase the motions of Brownian particles, so I will denote this side. So this side I always denote the increases, okay. So that means the third point is increase the temperature or higher the temperature, okay, higher the temperature, greater the motion. So that because the kinetic energy increases, so higher the temperature, the kinetic energy increases, okay. So even increase the temperature, your kinetic energy increase, and that increase your motions, okay, increase the motions of the particles. So now in the options, what is in the options? So let's check. Yeah, so in which case the motions of the Brownian particle is greater? Higher temperature, higher viscosity, higher size of the particle. So this is not true, because we just see that the size of the particle must be reduced, okay, in order to increase your motions of the Brownian particle. Higher viscosity, this is also not true, but the higher temperatures, so this one is true, right? So the option A is correct. So if B and C is not true, so that means the last one is also not true. all of that. Okay. So this is also not true. So the only option A is correct. Okay. So only one option is correct. Yeah. So far any question. Okay, so since there is no question, so I will move to the next one. So in pairing works, in order to study Brownian particle, in order to study Brownian particle, the photograph of the particle movement were captured periodically, the real-time particle trajectories were drawn by hand, the particle positions were drawn by hand at a given time interval, and the particle number were calculated from the captured photographs. This is just a statement. If you look into the class notes, okay, you already answered these questions, so there is no calculations. Okay, so we know that the pairing works in order to study the Brownian particles. Okay, so the particle positions were drawn by hand at a given time interval, right? So recall your class notes. Okay. So the option C is correct. Okay. So the particle position were drawn by hand at a given time. So that is the pairing methodology. And okay, so then I move to the next one. So the next question, the ratio of Avogadro number, okay, as measured by pairing is NA pairing, right? So NA pairing, that is measured by pairing. Okay, and modern day accepted value is NA modern. Okay, and their ratio is R. So NA modern. So this is, we know what is the modern day expected value is 6.022 times 10 to the power minus 10 to the power 23. Okay, so this is NA modern, but we do not know what is the NA pairing. Okay, I mean, if you look into the class note, okay, so the NA pairing or the pairing experiment, so pairing is successive times measure this the value of the Avogadro numbers. Okay. So he got the values of the Avogadro numbers, okay, NA slightly higher, so 6.89 times 10 to the power 23. Okay. And we know the modern day expected value is 6.022. Okay, so slightly lower value, okay. And pairing got a higher value. Okay. So then the ratio R obviously greater than 1, right? And the later in 1910, so this pairing, observe this is basically 1909 to 1915. Okay. So they start to measure this value of the Avogadro number 1909 to 1915. Okay. And 1923, 1926 he got a Nobel Prize, and 1910, okay, Millikan and what is the other name, the Millikan and sorry, yeah, Millikan and Fletcher. Okay, so Millikan and Fletcher, they also measured this value. Fletcher. Okay, so they also measure the value of the Avogadro numbers. Okay, Na. So the concept of Brownian particles, measure the charge of an Brownian particles, right? So they got Na is basically 6.05, again slightly higher value, okay, from the modern day expected value. Okay, so 6.05 times 10 to the power 23. Okay, so again the ratio is greater than 1. Okay, the pairing work is definitely greater than 1, but the 1910 the the experiment by Millikan and Fletcher. Okay, they also got slightly higher values. Okay, 6.05. Okay, so then the option D is correct. Yeah, so the last one. Yeah, so far any question? Okay. Okay, so if not, then I will move to the last question. Okay, so gas or molecular weight m. So this is a molecular weight, right? Is kept in a column of height h at a temperature T. Okay. The pressure and the number density at the base is Z0, P0 and N0. At what height the number density falls to 1 over E. So how the number density changes with height or the pressure changes with height. So you know that the P is basically P0. So P at height, let's say H is PH or P. Okay, let's say PH equals to P0, the base value, time the changes e to the power minus m. M is the molecular weight, mg, and then h. Okay, and I say that the base is 0. Okay, or you just replace, sorry, h minus h naught, your base height. So base height is h naught and at height h, so h over h naught divided by RT. So here I am using R, the gas constants, because the molecular weight is m. So basically capital M is Na times small m. Okay, where Na the Avogadro number of molecules are there. Right, you consider the Avogadro number of molecules are there. So Na times small m. Okay, so the mass of these particles. So that's why if we multiplied both sides with Na, so it gives this. So if we replace with the number density, so N, so the number density and pressure are the proportionality. So NH is also N naught e to the power minus m g h minus h naught over RT. So this NH is given in the problem, it's 1 over E. So at what height the number density fall as 1 over E. So this is basically, so if the base height is the number density at the base means that h naught height, so is the base, so it's n naught over E. So this is at height, let's say h. So I have to calculate h. What is the values of h? Okay, where the number density n naught by E, right? So problem is clear. So at what height h, so the number density nh is n naught over E. So number density falls as 1 over E. So I have to calculate h. So that means n naught over E is e to the power minus m g h minus h naught over RT. So that means n naught, sorry, here is n naught, so n naught E inverse equals to n naught e to the power minus mg h minus h naught over RT. So compare the power of exponential, because n naught cancel, sorry, this one is n naught, so n naught cancel, so this one is to the power minus 1 and this is basically this. So if we compare this, so your m g h minus h naught over RT equals to 1, right? So compare the power of, or equate the power of the exponent. Okay, so it gives h minus h naught is RT over mg So H naught plus RT over mg. Okay, so let's see that if this is in the option or not. Yeah, so now the base height is z naught, so here H naught is basically z naught. Okay, and at the height, at what height? So basically H. So I just replace this H naught to z naught. Okay, according to the problem. So therefore the z naught plus okay, I replace everywhere is z naught. Replace everywhere is z naught. Z naught. Yeah, now it's okay. Yeah, so the answer is z naught plus RT over mg. So yeah, so option A, z naught plus RT over mg. Okay, so you can also check by dimensional analysis. Okay, so RT over mg or mg over RT. Okay, so you see that there is a two option is mg over RT. So if we check the dimension, so this mg over RT, the dimensions of mg over RT is basically dimensions of 1 over length x. Okay, so that means you cannot add with the length, right? So because the length of 1 over the 1 over length and length cannot add. Okay, so the same dimensions number are add. Okay, so when you add two numbers, so the dimensions of this sorry, the two quantity, when we add two quantity, the dimensions of this two quantity must be same, otherwise you cannot add or subtract. Okay, you can multiply but you cannot add or subtract two different dimensions quantity. Okay, so that means this option is incorrect, this option is incorrect. Okay, so now from A and B, so you have to check the sign. Okay, so now to do this, so you have to calculate the full calculus. So the option A is correct, so with a plus sign. Okay. Yeah, so far any question? Okay, so there is no question. Since already about 30 minutes left, so I'll discuss some basic concept then about the Brownian motions. Okay, so what is Brownian motions and how it's related to the diffusion equations? That is very important. So basically the problem is that how the irregular movement, so Brownian motion is basically a random motion, right? So it's irregular movement. So how the irregular movement so how the irregular movement of a particle suspended in a liquid, okay, related to the diffusion equations. Right, so you know what is the diffusion equation, right? So what is the diffusion equations? Okay, so let's first write down the diffusion equations. Del F xt in position and time, x is position and t is time t, and f(x_t) is the distributions function. So f of x_t is the distribution function, and this is the diffusion equation. So diffusion equation in 1D, okay, because we are considering only x, the position, 1D position. So del f del t is equals to d times the second derivative in the space. So first derivative in time and second derivative in space, that is important. Okay, and there is no minus sign with plus sign, and the coefficient is the d is called the diffusion constant. Okay, is the diffusion constant d. And these equations, so what is the meaning of the diffusion equations, or yeah, so what is the role of these equations? Okay. So these equations describes the evolutions of the distributions of particle in space and time. Okay. So this equation describes the evolution of the distributions of particles in space and time. Okay, in space and time t. Okay. So what is the solutions of this function, how the distribution functions look like? So for that we have to solve these equations. Okay. So this is a differential equations, okay, and you know that how to solve the differential equations, right? So once you solve the equation, so the distribution functions f of x_t get n over, so n is the normalization constant, 4 pi dt. So this, sorry, n is the number of particles and n by 4 pi dt is the normalization constants, then e to the power minus x square over 4 dt. Okay, so it's basically an exponential function. So and this function of both x and t. Okay. The exponential both x and t, but the power of x is square and t is 1. Okay, and because the nature is that, so the time derivatives with respect to the first order in time and the second order in space. So now you just quickly calculate the x average. So once you know the distribution functions, how to compute the x average, as you already do in the Maxwell-Boltzmann theory, right? So once you know the velocity distributions, you calculate the velocity average, v square average. So in this case, once you know the distribution functions f of x_t, you can also calculate the x average using these distribution functions, which is basically your limit of x is minus infinity to infinity, all in the 1D from negative to positives. So minus infinity to infinity x times f of x_t times dx, and by the normalizations, right? So if x_t is normalized, then the denominator gives 1, but if it is not normalized, then you have to divide it by the normalizations factor. Okay. So it gives 0 because this is a even function in x and this is an odd functions. So when you multiply it, so f of x_t is an even function in x, and the x is the odd functions, but you have to integrate over a symmetric interval minus infinity to infinity, so it gives 0. But if you calculate the x square average, right, so it gives 2 dt. This is a non-zero number, okay, because now the x square is an even function, so it cannot give 0 from the symmetry argument. So So if you calculate the root mean square distance, so lambda, let us say RMS, is basically x square average minus x average square, so that gives 0. This basically square root of x square average, so square root of 2 dt. So that means the RMS distance is not 0, even if the average velocity is 0, sorry, average distance is 0, but the RMS distance is lambda, let us say lambda RMS, okay. So that is not 0. Square root of 2 square root of 2 times d times d, time is depends on time, okay, and d is the diffusion constant, okay. So this is the typical characteristics of Brownian motions. So that means the RMS distance is not 0, even. So basically if you consider random fluctuations, right, so random fluctuations about the origin, about the point 0, and it gives in the positive negatives, okay. So the average value is 0, okay, as expected, okay, for any random motions about the origin the average value is 0, but the x square average or the RMS is not 0. So this is the typical characteristics. This is the typical characteristics of Brownian motion. Is a random motion. Right. So now the question is that the irregular movement of the suspended particle in a liquid are connected by the thermal motions of the molecule of the liquid. So therefore, so this irregular movement of the suspended particle irregular movement of the suspended particles in a liquid are caused by the thermal motions of the molecule of the liquid. So this is a Brownian motions. The irregular movement of a suspended particle in a liquid is a Brownian motions. Okay, typical example of Brownian motions are caused by the thermal motions of the molecule of the liquid. So what is thermal motion? Thermal motion of the molecules of the liquid. So these thermal motions of the molecules, what do you mean the thermal motions of the molecules? So this is basically the existence of random force. So this is basically the existence of random force. So what do you mean? Okay, I will come into this point. So what do you mean the random force? So suppose that we impart to a particle that is suspended in a liquid certain velocity v by a force applied to it from the outside. Okay, so suppose that we impart to a particle that is suspended in a liquid and we impart to the particle with a certain velocity v. So certain velocity v, okay, by a force. So how to impart this velocity? By a force applied to it from the outside, applied to it from outside. So therefore the force is m dv dt, Newton's law, right? So m dv dt, this is equals to force, that is exactly equals to your drag force, right? So what is the drag force in the medium where the particle suspended in a liquid in that medium, right? So what is the drag force? That exactly equals to minus of drag force 6 pi eta rv, right? So this is your drag force, this is your drag force or the viscous force, right? So here eta is the viscosity, v is the velocity we know, okay, and the r is the radius of the particle. So I am not writing this thing. So now we solve these equations, okay. So this is your first order equations in v, so m dv dt, and there is a right hand side also v, okay. So once you solve this equation, so equation is basically m dv dt equals to minus 6 pi eta rv. So this is your first order equations in v. Once you solve this, v is v naught times exponential minus 6 pi eta r over m times t, right? So let's say t equals to 0, where the velocity v equals to v naught, okay, and by certain velocity v at time t, okay. So they follow this equation, okay. But we know from the kinetic theory, so this is the velocity, right, changes if we put an external force on it, right? But we know from the kinetic theory, so what do we know from kinetic theory? So now we know from the kinetic theory that we know from kinetic theory that if we fix the temperature, okay, so your average energy is 3/2 kBT at absolute temperature is T. So this is a fixed. So when you fix the temperature T, your average energy 3/2 kBT. Now this average energy is basically what? Now half m v square, right? V square average. This average energy is the kinetic energy, E kinetic, and E kinetic is half m v square, the kinetic energy, right? So this gives half m v square average is 3/2 kBT, right? So therefore the v square average is 3 kBT over m, right? And square root of v square average, square root of 3 kBT over m, which is not equals to 0, or it basically constant, sorry. So it gives a constant value at temperature T. So it gives constant at certain temperature T, right? Certain temperature. So when we fix the temperature, right? So the v square average, the square root of v square average, okay, it gives a non-zero value, right? But we see that the velocity changes with time, right? So the velocity changes with time, but from kinetic theory you know that this is constant, okay, if we fix the temperature. So that means in order to maintain in order to maintain the average, in order to maintain this, I mean the square root of v square average, the particle must experience the impulses, the particle must experience the particle must experience impulses or impulses sorry, impulses from the liquid molecules, okay, whose directions and magnitudes are random. Impulses from liquid molecules whose directions and magnitudes are random, which directions and magnitude are random. So this is basically the random force. Okay. So in order to balance this, the v square average, in order to maintain the v square average, the particle must experience some impulses from the liquid molecules. Okay, that is whose directions and magnitudes are random. That is basically a random force. Okay, in order to balance this. So therefore, this random force, so there must exist a random force Ft acting on each particle. So there must exist a random force, let us say Ft, time dependent force, okay, because the velocity changes with time, right. But we know that in order to fix this is a constant, is independent of time, okay. So we need a random force. So this random force F is also time dependent, okay, and there exists a random force Ft acting on each particle, okay, such that this Ft average is 0, okay, and Ft square average is not 0. So this average is time average. So this average is time average, because again it is a random, so the average value is 0, but the square average is not 0, right. So then the modified equations of motions, so then these equations of motions is modified, right, because v does not fall exponentially with time, okay. So there must be some random force, okay. So then the equations is modified. So the modified equations of motions is m dv dt equals to minus 6 pi eta rv plus random force Ft. So you have to add a random force, and this is your modified equations, okay. Okay, and that is free from any external force, that is free from any external force, right, because the external force is actually equal to the drag force minus 6 pi eta rv. So that is free from any external force, okay. So this is the Langevin equation of motions, okay. So this famous equation is known is the Langevin equation of motions. So this is the Langevin equations of motion, okay. right? Okay, so the conclusion is that thus the perpetual motions of the perpetual motions of the Brownian particle is maintained by the fluctuations in the collisions, is maintained by the fluctuations. So that is basically random fluctuations in the collision with the molecules of the surrounding liquid. The fluctuations, so this is basically random in the collision with the molecules right, of the surrounding liquid. Surrounding liquid. Okay. So there are basic assumption is that, so one is Ft is independent of velocity. So this the fluctuations or the random force Ft is independent of velocity, right, and Ft average, since it is random, so the average is 0, and second is Ft varies extremely rapidly compared to the variations of the velocity. Ft is independent of the velocity, but Ft varies extremely rapidly compared to the variation of the velocity. Variation of the velocity. Okay. So if we consider a time interval, so let us say time interval tau, okay. So variations of the velocity is small, but Ft may undergo many fluctuations. So in a time interval tau, the variation of the velocity, let us say small. Okay. So in this time interval tau, okay, so let us say we consider time interval tau where the velocity is not changes too much. Okay. So the variation of the velocity is small, but the fluctuations or the random fluctuations, okay, but Ft is the fluctuations, okay, may undergo many fluctuations, may undergo many fluctuations. Okay. So that is mean that is the Ft vary extremely rapidly compared to the variation of the velocity, right. So if there is a small change in velocity, but Ft may undergo many fluctuations. So, yeah, so so far any questions? So that's all I will plan to discuss today. Yeah, so so far any questions? You can also write in the chat box if you have any questions, or you can also raise your questions in the discussion forum in the course portal. Okay, so I hope you will able to solve the assignment 4 problems this year. Okay, so that is, I mean, the deadline coming soon. Okay, so if you have not any more questions, then I will stop here. Okay, and see you in the next Sunday at 4 p.m. Okay, thank you. Bye bye.